Hi, my name is Cherelle Connor, and on behalf of my research team, I'll be presenting our work titled Reevaluating Virtual Reality Manipulation Techniques for Precise Alignment of Complex 3D Objects. So VR has emerged as a promising medium for tasks related to additive manufacturing. Virtual representations of 3D printed parts can be aligned with computer-aided design models or CAD models for visual defect inspection within virtual environments. So this type of alignment typically requires a high level of precision in order to accurately assess the quality of the 3D parts. However, there are few manipulation techniques that offer the level of precision required for these alignment operations, and this reveals an ongoing challenge of designing effective interaction techniques for precise manipulation in VR environments. Prior manipulation techniques such as Prism, GoGo, and virtual widgets have been instrumental in spawning novel approaches to precise manipulation within VR. The evaluation of these techniques, however, is often assessed using just a simple geometric object, and this motivates our research aim of understanding how these techniques perform when applied to the alignment of a more complex object. In particular, we build on the work of Rodrigues et al., who developed two novel techniques for high precision alignment in VR. These techniques were the AMPIT technique and the Wisdom technique. Their previous work evaluated the techniques using a simple box object and found that both AMPIT and Wisdom achieved better performance when compared to the techniques previously mentioned in the literature. So in their work, Wisdom emerged as the more effective technique for high precision tasks, and participants not only had better performance with the technique, but they also preferred Wisdom in terms of usability and felt that it reduced workload. And while their experiment provided valuable advances towards addressing the challenge of precise manipulation in VR for alignment, the use of the simple geometric object does not comprehensively represent the challenges that can be posed by a real-world alignment task. Alignment tasks of complex objects can be harder to judge visually and may be difficult for participants to understand how to use the individual degrees of freedom to achieve their desired alignment. So this leads us to our following research questions in which we wanted to validate the results of Rodrigues et al.'s prior work with a geometrically complex object in terms of performance, usability, workload, as well as preference. We conducted a within-subject study and collected data from 25 participants. Our virtual environment was developed using Unity, and the participants used the MetaQuest 2 headset and controllers in order to visualize and interact with a virtual object. We had two independent variables, technique and difficulty, which each had two levels. So technique had AMPIT Wisdom, and difficulty had easy and hard trials. We also had dependent variables in the form of performance, which was defined by task completion time as well as clutch count. And clutch count refers to the number of trigger button presses that the participant needed in order to complete that trial. We had workload in the form of the NASA TLX, usability in the form of a custom usability scale, and preference in the form of a post-study survey/interview from which we also collected qualitative data. So in the virtual environment, participants were tasked with aligning a manipulation object, which was an opaque gray object with its translucent target. Participants completed the alignment task with two levels of difficulty, easy and hard, using each of the techniques. For the easy trials, the target size was 10% larger than the manipulation object, which allowed for a large margin of error for task completion. And for the hard trials, the target was 1% larger, which reduced the margin of error and thus made the trial more difficult. Participants would continue the alignment process until the manipulation object turned green, which would signify that it was successfully aligned. Now let's further discuss the techniques used in this work. Both of the techniques were designed in accordance with Rodrigues et al. Specification. The AMPIT technique was based on the Prism technique and uses an exponential function to smooth transitions and minimize unintended movements by filtering out motion resulting from hand instability. AMPIT dynamically adjusts the control display ratio based on hand speed, with fast hand speeds corresponding to quick movements and slower hand speeds corresponding to slow, more deliberate movements. Wisdom combines both the direct and widget-based manipulation. So the direct manipulation mode of Wisdom provides a one-to-one mapping between the user's physical hand and the controller of the virtual environment. whereas the widgets mode provides scaled mapping for each of the 6 individual degrees of freedom, which can be controlled one at a time. And during the study, users were free to switch between these 2 modes of manipulation as they so choose. So participants completed the task faster with AMPIT for both the easy and hard trials. They also used a greater number of clutches in both the easy and hard trials. Revisiting our initial research question, which concerned performance, we found that AMPIT outperformed Wisdom in the hard trials. And even though AMPIT had higher clutch counts or required more button interactions, this did not impact the participants' performance with the technique. So this is actually contrary to those previous findings by Rodrigues et al., in which they found that Wisdom trended towards superior performance in their hard trials. Revisiting our second question, which concerned usability and workload, participants found Wisdom to have a greater overall usability when compared to the AMPIT technique. They also felt that Wisdom was better for rotation. However, they did feel more confident while using AMPIT. The participants also attributed more workload to the Wisdom technique, and they felt significantly more frustrated and that their performance was poorer while using Wisdom. So our study found that Wisdom was more usable, however associated with greater workload. And similarly, the previous work found Wisdom to be more usable. However, they did not find any significant difference between the Wisdom and the AMPIT techniques in terms of workload. We observed that there were significantly more participants who preferred Wisdom to AMPIT for natural rotation. And out of our 25 participants, this was a 20-5 split. This finding is aligned with what was previously identified in Rodrigues' work. In our case, however, this preference implies an interesting disconnect between objective performance and subjective experience, and suggests that comfort as well as intuitiveness may carry more weight in user preference than actual performance metrics. From the qualitative data collected via our post-study interview, we identified 3 main themes: axial control, axis visualization, as well as movement sensitivity. In the table shown here, there's a summary of the negative relationships between the themes identified and the individual items of the post-study questionnaire. And so this is just to add some color to some of the quantitative results discussed previously. For instance, if we look at the AMPIT technique, participants expressed that they were uncertain of how the object would move due to a lack of visual feedback during rotation. However, they also expressed that the explicit visualization of the rotational axes made it difficult for them to view the object's position and complete their alignment task. Similarly, for movement sensitivity, they expressed difficulty using AMPIT. They expressed difficulty predicting the rate of movement required in order to move the object. Again, AMPIT had this particular hand mapping. However, they also expressed that having the one-to-one direct mapping increased potential for errors due to hand instability. So this is just an example of some of the trade-offs between each of these techniques. Overall, the AMPIT technique performed better than Wisdom when manipulating a complex 3D object. The visualization of the axes for the Wisdom technique with its spheres and circles contained much more visual information, and as suggested by the participants during the qualitative analysis, that additional information may have hindered their ability to understand the misalignment that was occurring between the object and the target. Additionally, having more intricate details required for alignment may have contributed to an increased task workload throughout the trials, specifically, again, in the case of Wisdom, in which the individual axial adjustments were found to be more challenging. Either way, having an intuitive and natural method of interaction did provide participants a level of familiarity that allowed them to focus on task completion rather than figuring out how to actually manipulate the object with the technique. Our analysis revealed design considerations for improving precise manipulation in VR environments with a complex 3D object. We found that techniques may benefit from context-sensitive access visualizations. And again, as suggested by our qualitative data, having a level of control of the amount of visual information that they're receiving at one time would be beneficial to allow them to more effectively complete their alignment tasks. Additionally, we found that adaptive sensitivity may aid in balancing user performance as well as preference, and specifically movement sensitivity. So being able to complete large, broad sweeping movements that don't require a large amount of precision, and then dynamically switching to slower, more deliberate manipulation techniques when that higher level of precision is required. And through our comparative study of these techniques, we partially validated the findings of previous literature and also identified important distinctions that emerge when users interact with the complex geometry of a real-world object rather than a simple geometric shape. We also emphasized the importance of considering both performance metrics and user experience when designing VR interaction techniques for complex 3D object manipulation.